Social scientists are increasingly turning to artificial intelligence to automate their research. They are using large language models to code massive datasets and simulate thousands of voters in a fraction of the time it takes human researchers. On the surface, the output is convincing. A prompted model can generate simulated survey responses or text classifications that perfectly mimic authentic human political speech. But a severe paradox emerges when we treat these outputs as actual data. When researchers plug these LLM-generated variables into standard causal regression models, the underlying math breaks down. A large empirical evaluation by Yang and colleagues found that replacing human-coded variables with LLM-generated ones leads to wildly shifting coefficient estimates. Point estimates cross zero, and standard errors expand dramatically. This instability persists across different model versions. It is not an engineering bug that can be resolved with a slightly rephrased prompt or a different random seed. The failure points to a category error. Researchers are treating systems built to generate plausible language as if they were scientific instruments measuring social reality. The current methodology relies on a specific assumption. Because political reality is expressed through language, a model that has mastered the statistical structure of language provides direct access to that political reality. But human language production is a strategic, performative act. When people speak or write online, they construct identities and respond to social desirability pressures. The text they leave behind is not a transparent record of their private beliefs. Scaling up the training data does not neutralize these distortions. Feeding a model a larger text corpus simply bakes these systematic, intentional biases into its foundation. Counting words in a dataset is different from surveying individuals. The frequency of a word in a training corpus does not equal the frequency of a belief in a real-world population. Human behavior is a complex, organic process. Autoregressive models compress those actions into rigid statistical patterns, optimized for predicting the next likely word. The language model has learned the distribution of words across documents. That is entirely decoupled from the actual distribution of social phenomena across human populations. To understand why language models fail to produce empirical evidence, we have to look at the work of 19th century philosopher Charles Sanders Peirce. Peirce developed a tripartite theory of signs that maps exactly onto the structural gap in AI data. The most crucial category in his framework is the index. An index is a representation that is physically or causally connected to the object it represents. A thermometer reading is an index because the mercury is physically constrained by heat. A footprint is an index because it is caused by the physical pressure of a foot walking through mud. A real human survey response is causally tethered to an individual's cognitive state. When the person's belief changes, the response changes. But language models fall into the symbolic category. Their outputs rely on learned statistical conventions, lacking any causal link to physical reality. When a language model generates a simulated survey response, that output is caused by the statistical likelihood of prior text strings in its training data. It is not caused by the real-world event the text describes. Without that causal indexical tether, a representation cannot act as evidence. Models simulate political speech well, but they generate symbols, not indices. Traditional machine learning tools like regularized regressions function as true statistical estimators. They approximate a relationship by minimizing error against an observable target outcome in a real population. Autoregressive language models structurally lack this structure. They do not sample from a population or minimize error relative to a measurable social scientific quantity. They optimize for next token prediction over text corpora. A recent study by Han and colleagues on the personality illusion proves the consequences of this structural failure. They found that engineers can use reinforcement learning from human feedback to train a model to generate stable self-reports of psychological traits, like agreeableness. The model produces a stable upward trend in self-reported traits, yet when tested in cooperative tasks, those self-reports have zero predictive power. The system hasn't developed a hidden psychological disposition, it's merely been trained to adopt a surface-level linguistic habit. Internal coherence in an output is a property of the language model itself. We cannot mistake it for the measurement of a genuine social phenomenon. A common defense is that human coders also suffer from fatigue or cultural bias, and we should simply treat language model outputs as noisy data, requiring standard measurement error correction. In classical test theory, observed measurement equals true score plus error. With human fatigue, the error fluctuates, but the true score remains stable. Apply this to language models, and the equation collapses. Altering a prompt doesn't just increase error, the entire measurement instrument shifts. Human measurement degrades in mathematically predictable ways. Language models shift unpredictably because they lack a fixed identity across versions. Because the relationship between the model's output and the target concept changes invisibly, there is no stable true score foundation to anchor it as a measurement tool. If these models lack indexical grounding and fail as statistical estimators, are they entirely useless for rigorous social science? Large language models possess utility for research, provided we move away from inductive justification and toward theoretical generation. Peirce outlined 3 modes of scientific inference. Induction tests hypotheses against evidence, deduction derives logical implications, and abduction generates the explanatory hypotheses in the first place. Abduction is the creative leap that proposes structural explanations for puzzling patterns. Of the 3 modes, it is the only one that explicitly does not require an indexical tether to physical reality. Language models excel at abductive reasoning. They hold massive cross-domain networks of linguistic associations that are unbound by physical constraints. Recognizing an LLM as an engine of conceptual translation rather than a tool for measurement locates its appropriate role in the research workflow. We can see this conceptual translation in action through political scientist Michael Choi's work, which maps Jane Austen's literature directly into formal game theory. The primary narrative tension in Pride and Prejudice is a lack of credible information. Characters cannot reliably discern each other's true intentions, and verbal declarations alone carry no weight. An LLM can rapidly map this literary tension onto the structural features of a strategic signaling game. Darcy's first marriage proposal costs him nothing to make. Therefore, in game theoretic terms, it is cheap talk. It reveals absolutely no reliable information about his character. As the narrative progresses, Darcy writes a detailed letter. The language model structurally identifies this as a semi-separating signal, an action requiring effort that narrows the ambiguity of his intentions. The narrative peaks when Darcy privately spends significant financial and social capital to save Elizabeth's family from scandal. The model maps this directly to a causally signal, achieving what game theorists call a separating equilibrium. The language model is not offering empirical proof that signal theory governs human courtship. It is rapidly identifying structural parallels across 2 entirely different domains. This defines the boundary for researchers. The process of discovery must remain separate from the process of justification. Language models are collaborative engines for generating theory, but they are not autonomous instruments of measurement.